Hi class, this is your video lecture for physics on Monday, September 14th. Today we have a couple topics about some fundamental things in physics, one of them being position and the other being velocity. So we're going to talk about some variations of those today. First, I want to start off with position. And there's a couple different variations of position. We have position, we have the distance, and we have displacement. So let's talk about each of these in a little more detail. Position, if I give you a definition, this is the location of the object at a given moment in time. The location of an object at a given moment in time, right? So oftentimes we're used to doing this with a map, right? We'll have some sort of coordinate system, and it'll help us say, well, it's so many degrees east or so many degrees west, so many degrees north or south. Or we have you can also just think of it as a graph that you use in your math class, right? You have your X and your Y coordinate system, and you want to say, what's the position of a point? You would say X equals 3, Y equals 5, right? So then when we're talking about position, we have the location of that object, but we have to have it with reference to some sort of a coordinate system, right? Otherwise, it doesn't mean anything. It points here, so where is that point? You need something to back that up. Now, a position can be positive or negative. Just like on your number line in math, you can have negative numbers and positive numbers. Okay. Now, our initial position, our starting position, we're going to label two particular positions. This is the position you are when you start your trip. We'll call this the initial or the starting position. Sometimes you'll see this written in a couple different ways when we put it in our math. Sometimes it's an x0 or an x0, you might hear me say, or an x1 or an xi for initial. But I'm going to try to stick with x0, x0. I want to contrast that with the final or the ending position. We're going to call this is where you end up on your trip. And we're going to use a very similar symbol for it. We're going to have x, and we're going to have a little f after that for our final position. Okay. So all I've done is define two points. Where do you start and where do you finish? Let's take that a little bit further. So now we can define position. How are we going to define distance? Well, let's use the definition of distance as how much ground an object is covered during its motion. Right? So that might be simple motion where it just moves from point A to point B. It might be a much more complicated motion where it goes from point A to point B to point C to point D to point E, and maybe even coming back to point A. Right? So there might be different legs of our trip. All right, but our distance traveled is going to depend on our entire trip. And how do we figure out what that is? We're going to add the distance of each leg of our trip separately. Right? So for example, if I leave my house and drive to school, I've traveled 5 miles on that leg. If I drive back home, I've driven another 5 miles on that leg. So my total distance is 10 miles. My distance depends on the entire trip. Now, distance is always going to be positive. It's always going to be positive, right? So what we're going to do when we're trying to find the distance of one segment of a trip, right, we're going to take that final position and we're going to subtract the initial position, and then we're going to take an absolute value. So what I'm saying is there's distance. It doesn't matter which direction you're going, right? I didn't say I traveled a negative 5 miles from my house down to school and then a positive 5 miles back up. That doesn't quite make sense when we're talking about distance. It will for our next term. But for distance, all we want to know is what are the 2 points and what's the subtract one from the other and take an absolute value, right? Just make it a positive number. The value, or the symbol rather, that we're going to use for distance is just simply a d. So if I write a math equation and you see a d, you know I'm talking about distance. Okay. Let's talk about another one that's called displacement. This is a little more complicated, so I want you to be thinking about this. It's a little bit more unnatural, I guess I should say. But when you think about it, you'll realize, oh yeah, we deal with that. So I'm going to define displacement as how far out of place an object is. In other words, what was its overall change in position? Now, this only depends on our initial and our final position. It doesn't matter what happened in between. So if I went from point A to point B to point C to point D to point E, all that matters is we ended at point E, we started at point A, how far apart are those 2 points? Doesn't matter how we got there. Now, similarly, if we started at point A, went to point B, point to C, and came back to point A, what's our initial point? A. What's our final point? A. How far did you go? Nowhere. Your displacement was 0 because you ended up where you started. Right? So we're probably used to both of these kinds of concepts, but in physics, we're going to really make sure we understand the difference between them. And it's not just simply a technical or a math description. It is important when we're doing our calculations and understanding what's going on. Okay. So again, displacement, just how far it's overall, how far it's changed, how far it's moved. And we're going to we'll oftentimes take x final minus x zero, x naught. And I put this one in parentheses, not in the absolute value bars, because it does depend on which direction you're going. It does depend on which direction you're going, right? Now, it only depends on the final and initial positions, but it does depend on your direction. So it could be positive or negative, right? So if I left school and went to my house and I lived almost straight north, right? I could say that's in a positive direction. I went up, I went north. But if I went the other direction, if I went south, I could say that I went down or I went a negative direction. So displacement always has a direction. Always has a direction. Distance doesn't. So again, think about, well, let's think about going around the square. If we go around the square, we go a certain distance to this way, certain distance this way, certain distance this way. We're just going to add up each of those legs. It doesn't matter which direction they went. Whereas if we wanted to figure out the displacement, right, it only matters where we start and where we end. Right? So it doesn't matter how we got there. It just matters how we start and where we end. And also, it's that direction. So if we started here and ended here, I would draw an arrow pointing up. Right? An arrow pointing up. Right? It depends on your XF and X naught are very important here. You got to make sure you understand which one's your starting point and which one is your final point. Now, we'll usually call this, it helps if I get the right tool. We're going to usually call this delta X. That triangle in front, that's the Greek letter delta, and that triangle means difference, a change in X, or simply this is XF minus X0. And again, the order here is important. X final minus X initial. 2 more thoughts on this slide before we go into some examples of using this information. The SI, or the metric unit for position and distance and traveled or displacement, it's meters. We're going to use meters for the most part in physics class. We could also use centimeters, and we could even use kilometers for that matter. So hopefully this is maybe just a little different than what you've thought of before. The biggest thing I want you to get out of it is the distance is just how far you went, right? So if you were a track athlete and you ran around the track once, it'd be 440 meters would be your distance. But your displacement, if you made 1 lap around the track, you ended up where you started, your displacement would be 0. All right. So I want you to make sure you understand the difference. Right? Displacement does not care how many different legs you do. You're just taking the final minus the initial. Distance does. It depends on how many legs you do because you got to add up the distance of each little leg. So let's put these into solving some problems. I got 5 problems here real quick we'll talk about. So what's our problem here? For each situation we describe, we're going to state the initial position, x0, x naught, the final position, xf, the distance we traveled, d, and the displacement, delta x. Now, the instructions also suggest that it might help to sketch a number line and include our units as well. Remember, we don't want to have naked numbers. Every number should have a unit. So let's start off and let's draw our number line. Let's see if I can get it to pop up here. There's our number line. And where did we start? So I'm going to label the number line. We started here, x0 was at 12. All right. Where do we end up? At 5. So I'm going to put an xf above our 5 on our number line. Now I'm going to draw an arrow connecting them. I'm going to start my arrow at x0 and end my arrow at xf. It helps us understand the direction we moved. Very important. The direction is very important for displacement. So we already used this number line to help us understand things. We already labeled x naught, that's 12. We labeled our final x, that's 5. What's our distance? I'm going to take 5 where we ended up, 5 meters minus 12 meters, and we're going to take the absolute value of that. Right? So the difference between those two is going to be -7. Take the absolute value, and you're going to have 7 meters. So our distance was 7 meters. Displacement, on the other hand, does not, I'm not going to put the absolute value signs here. It does depend on the direction. We're going to do 5 meters minus 12 meters, and this time we're going to get -7 meters. So while distance is positive, it'll always be positive. Displacement may be negative, it may be positive. Now that was a real simple one, right? We took one leg on our trip and our leg went to the left. Let's try this again. Let's do another example. A truck drives from 40 feet to -40 feet. So let's put our number line up in here. Let's put our x naught. I left my labels there wrong. That should have changed this to feet. I left it in meters. Sorry, guys. But at x naught, we're going to start at 40. And where do we end up? At 14. All right, so let's put, now that we've got our graph, let's label our values, our variables here. X naught, right? Started at 40. We finished up at -14. Let's do our calculation of our distance. -14 minus 40. Right? Our final minus our initial. So what that's going to give us, that's going to give us 54. 54. I'm going to take that absolute value. Now our delta x, our displacement, we don't take the absolute value. -14 minus 40, what's that going to give us? -54. So in both these scenarios, I want you to see that our arrow from x0 to xf went to the left, went in a negative direction. That's why our displacement, our delta x's here, are both negative. Let's make it a little bit harder here. This one is going to be, we're going to start thinking about positive and negative. Might just here is going to be north or south, right? Not just simply left or right, something like that. So we're going to be using south is a negative direction, north is positive. So let's put our number line in here first. And let's put in our x naught and our xf. So we're starting at 35 miles south. Well, if south is a negative direction, then our initial x, that's going to be down here. It's going to be on the negative side of our number line because it started south and south was negative. Now, this plane then flew to an airport in Dallas, 230 miles north. So that's a positive side. So we're going to put our xf over here at about 230. Let's draw our arrow to connect the two. Now notice that this arrow points to the right. This arrow points to the right. That's the direction we've called positive. Let's put in the values for our variables. Our x naught, our x initial was -35 miles. Where do we finish up at 230 miles? Again, let's calculate the distance. We're just going to take the difference of those two numbers. Let's take our final minus our initial, and then we're going to take the absolute value. Right? What's that give us in this case? 265. Now note when we do our delta x this time, our displacement. Start with our final, 230. We're going to subtract our initial, that -35. We'll also get a positive number here, positive 265. What I want you to see here is when our delta x, our displacement, when it's negative, our arrow is going to the left. When our displacement is positive, our arrow here goes to the right. Let's do another one. Football player starts at the 30-yard line. Let's put our graph in here while we're talking about it. There's our number line. Starts at the 30-yard line, so let's put our x naught in here. Runs to the 20-yard line. So let's put a red arrow here for a moment. I'll explain why it's red. Runs to the 20-yard line. Then the football player turns around and runs to the 45-yard line. So he or she ends up on the 45-yard line. So I'm going to put my xf over there. Now, I left those red arrows there for a reason, and we're going to see that when we talk about distance. So we know from our problem, from our number line as well, what's our x naught? Our x initial is at the 30-yard line. Where do we end up? We end up at the 45-yard line. What's our distance? Well, I have this first little leg here I showed you in red. We've got to find how far did the player run in that part. We're going to take our final spot, which was negative 20. I'm sorry, which was 20. And we're going to subtract our initial value where we started of 30. Right? Now, that's only one of the legs. We have another leg in this trip. And by a leg, it means our direction's changed. And we did another distance. So what's the distance of this second leg? Well, this one, where did the person end up? 45. So we're going to have our 45 here. Where did they start? 20. So we have our finishing point minus our starting point. Let's take those absolute values. Let's do that operation here. And what are we going to get? We're going to get 10 yards for this first one. We're going to get 25 yards for the second one. So our displacement's going to be, distance rather, is going to be 35. Here's where we're going to see a difference now. Displacement and distance are not going to have the same number, much less the same sign. So we saw the signs could be different up here. Problems 1 and 2, we had a negative number for our displacement, positive number for our distance. Let's take a look at it here. Where did we start? Our delta x, our displacement, it depends on where did we start and where did we end. So where did we end up? We ended up at the 45. Where did we start? We started on the 30. So our displacement is just looking at the distance between those 2 points. What's the distance between 45 and 30? That's 15 yards. Now I want you to see here, class, look what happened. Our distance, 35 yards, our displacement, 15. The number's not the same. The number's not the same. Whenever we have a trip or a route that has multiple legs, chances are these are not going to get the same numbers between your distance and your displacement. Right? Now, when you only have one leg, then yeah, you're going to have the same number. You might have a negative sign in front of your displacement, but you're still going to have the same number. As soon as you have multiple line segments, multiple segments to your trip, you're going to have different numbers, and you may also have a different sign. Your delta x, your displacement, might be negative. Let's do one more example here, guys. Let's talk about a child walking from a position of -8 to a position of 4, then back to 2, then back over to 10. Again, let's start off, let's put our number line in. And where are we starting? So we're going to start here at -8 meters. Right? Now our students then, our child then is going to move up to 4 meters. So here's an arrow. We're starting at -8. We went all the way up to 4. What did our child do then? The child then moved to a position of +2 meters. So it went backwards. It was at 4 and went to 2. So we've got our next arrow here going backwards. Finally, what's the last point after a child reaches position 2? The child then goes to position 10. So we got a third leg in our trip. If I can get that to show up. Third leg of our trip starts at the 2 and goes all the way to 10. All right. And finally, I should highlight our final position here, our XF. So let's put the values down here below. Where did we start? We started at -8. Where do we end? We ended at 10. How about our distance? You see, we have 3 legs in this trip, so we're going to have 3 terms. We're going to have 3 calculations to figure out our distance. What's the first one? Well, we're starting at, we started at -8. We went to 4. So let's do a subtract. Let's do that. Final position minus initial position. And we're going to take the absolute value. Well, that's our first leg. How about our second leg? What do we do in our second one? We ended at -2. We ended at 2, but we started at 4. Again, so we ended at 2, we started at 4. We're going to subtract them. And now we have to do our third leg. Right? We started at 2, we ended at 10. So we started at 2, we ended at 10. So now we've got all 3 legs of our trip. We've got them labeled out. Now we just do our calculation. Right? So for each one of these 3 terms, how far did they go? Right? So 4 minus -8, that's 12. It stays, we drop the sign, it stays 12. 2 minus 4, that'd be -2. Drop your sign, make it absolute value, and that gives you +2. And again, 10 minus 2 gives you 8. So how far was our distance, our total distance that this child walked? It's 22 meters. We just add all three of those legs together. Displacement, though, again, we got multiple legs, so chances are it's not going to be the same value. Let's highlight our displacement. Our displacement only depends on the initial position and the final position. Doesn't matter how we got there, just depends on the initial position and the final position. So what's our calculation here? Final position was 10 meters. Initial position was -8, so we're going to subtract them. What do we get here? We get 18 meters. 18 meters. So you can see displacement is different. Displacement is different. It depends only on the difference between the final and starting points. And it has a sign which tells you which direction you're going. In this case, we have positive 18, which agrees with our arrow. Our arrow is pointing to the right. Okay. Let's talk about velocity. Hopefully that one's not one that's too foreign to you. So we'll talk about velocity. What do we know about velocity? We're going to define velocity as the rate of change of position. Well, now that we understand position, that'll make it a little bit easier to understand velocity. What's our symbol we're going to use? V. And what's our units? Meters per second. Meters per second. Okay, how far did you go? How long did it take you to get there? Now, I want you to also notice that velocity has direction. Velocity has direction, and it's the same thing as the direction of our displacement. So I would say you might have a velocity of 35 miles an hour, but I have to have a direction onto that. So I'd say 35 miles an hour to the north, for example, right? That would be a velocity. So how are we going to calculate? Let's take this a little bit further. How would we calculate an average velocity? An average velocity. So we're going to give our definition of average velocity. It's simply the change in displacement, and we're going to divide that by the change in time. Remember, delta means change, right? So we can rewrite that as xf minus xi for our x naught for the top, and tf minus t naught for the bottom. But I want you to get comfortable with these symbols. We're going to use those delta symbols a lot. All right. Instantaneous velocity, though, is going to be a little bit different. This is the velocity of an object at a single instant in time, right? So it kind of makes sense. If I drove from school to my house, I'm starting at speed 0. I'm going to speed up to 35, 45 miles an hour, and then I'm going to slow back down to 0. I got to stop. So my average velocity is going to be the average of that whole trip. The instantaneous velocity is, what is your velocity at a single instant in time? Well, let's think now. Okay. So let's ask a question. Is it possible to measure the instantaneous velocity? And here you go. The answer is no. And why is it going to be no? Because the instantaneous velocity can never be measured, since there's no way in the real world to do anything simultaneously, instantaneously. You can't do it. Any measurement we take takes some amount of time. If I give you a ruler and ask you to measure something, you don't just slap the ruler down and boom, you have the answer. No, you're going to take a moment. You got to look at, where does it start? Where does it end? It takes you time to come up with that measurement. All measurements are that way. All measurements are that way. So it's not possible to measure an instantaneous velocity. We can calculate it. We'll do that later on. But I just want you to be aware we can't measure that. Now, I've talked about velocity. I want to talk about one more term here, and then we'll do some examples. And that term is going to be speed. What's the difference between velocity and speed? Speed is simply the magnitude of the velocity. So if I'm traveling in my car, if I'm going home and my speed is 35, and I'm moving at 35 miles an hour, my velocity will be 35 miles an hour to the north. What's my speed? Simply 35 miles an hour. It does not have a direction. Because it doesn't have a direction, if instead of heading north, I was going south, my velocity would be 35 miles an hour to the south, or a negative 35 miles an hour. What's the magnitude of the speed? It's still 35, right? Take the absolute value. That's what I mean by magnitude. So our speed's going to be still the same. So speed does not have direction. It's just simply the number, drop the sign, and that would take your velocity, drop the direction, drop the sign, and you're just left with a number, and that's what you're going to be for your speed. All right, couple quick problems here to show this example for velocity. Frog hops from a position of -8 centimeters to -18 centimeters over a period of 5 seconds. What's the frog's average velocity? Well, let's put our handy dandy number line on here. That's going to help us out a bit. Where did our frog start? X naught here is at -8 centimeters. Where did our frog finish? Over here at -18 centimeters. Now note that the arrow that connects, that goes from our starting point to our final point is to the left. So it's negative, means our direction's negative. If our direction's negative, our displacement's negative, our velocity will also be negative. Let's do our calculation. Delta x. This is our displacement, if you remember. It depends on the order here. Where did you end up? Where did you start? So let's put in our numbers. -18 minus -8. Our displacement's -10 centimeters. Good, it's negative. Our arrow's pointing to the left, so that's in agreement with our graph. So now we have our delta x. How do we get velocity? We have to divide our average velocity. We have to divide that by delta t. The problem tells us it took the frog 5 seconds. So let's take our delta x here, our displacement, our -10 centimeters. We're going to divide by our 5 seconds. And what are we going to get? -2 meters per second. Excuse me. Now again, notice our velocity has a sign. It has a direction. This was 2 meters a second in the negative direction, or 2 meters to the second to the left, if you will. Speed would not. If I asked you for the average speed here, you would just tell me 2 meters per second. You would drop that negative sign. We don't need a direction. Let's do one more. Car drives 40 miles due east. So typically we'll have east being a positive direction. East usually to the right when we're looking at something. And it took 30 minutes. What's the car's average velocity in miles per hour? I'm stressing that because we're given a period of minutes and we're asked for an answer in hours. So we got a little conversion we got to do here. What's our formula? The average velocity is our delta x divided by delta t. It told us what our delta x was, 40 miles to the east. East being a positive direction. So we're going to put 40 miles to the east. How long did it take us to get there? It took us 30 minutes to do that. But it's asking us for our velocity in miles per hour. So we got to do one more step here to answer that. We've got to take this from minutes and move it to hours. So we need that conversion. How many minutes are there in an hour? 60 minutes in 1 hour. Now, if you remember from chemistry or other class, remember, how do we know which goes on top here in this conversion term? 60 minutes or 1 hour. Which goes on top? You're going to know which goes on top because here minutes were in the bottom. We need minutes to be on the top over here so they cancel each other out. Then we're just left with a distance, 40 miles to the east, and a time, 1 hour. Okay, so let's put in our answer over here, and we went -80 miles an hour to the east. Again, velocity has a direction, and that's why we have the east here. All right, guys, hopefully that didn't overwhelm you too much, but that's a good starting point for what we're going to do in physics for the next several weeks. How do we calculate position, distance, displacement, and average velocity? All right, talk to you soon. Bye.